Thank you, Kathy, and good morning and good evening, everyone. My name is Chen Qiang, and I'm glad to be here to have this presentation and to share our recent research results. Thank you to Professor Wei Chenling and Kathy to invite me to attend this important conference. Today, my topic is also about the Zhihua Temple, but in a more technical way. The title is Digital Reconstruction of Beijing Zhihua Temple, a future exhibition. And this is our research team, worked in Nelson with Ling Anlu and Professor Wei Chenling. Thanks to my colleagues, Professor Jia and Ouyang, and all the graduate students participate in this project. As reported before, there are two sets of wood ceilings separately collected in the Nelson Atkins Museum of Art and the Philadelphia Museum of Art. Our project digital reconstruction, including both of these ceiling objects, because of the 3D scanning of Philadelphia Museum of Art, it's still under processing for the similarity of technical roadmap. As an example, this time I will mainly discuss the digitalizing reconstruction of the ceiling in the Nelson. My report consists of 3 parts below. And first, I will review the 3D scanning process of the Zhihua digitalizing project. And then I will show you the research on ceiling structure rebuilding and the reconstruction methods of the original ceiling installation environment. And then the last, a visual showcase of the research results will be presented. Okay, let's look at the first part about the 3D scanning. In technical view, it is a precondition and start point of the whole digital reconstruction project. I've introduced the work in 4 subsections below: 3D scanning object and work situation, scanning technique and strategy, scanning process and optimizing. Finally, I will show you some of the 3D scanning results. For the ceiling in Nelson, the most challenging task is to scanning the central main part of the ceiling. As talked before, the wood ceiling was originally installed in the Wanfege Zhihua Temple with small pavilion and cloud pattern decorated beams. To reconstruct the entire installation and cultural environment, we need to scan in both the relics in Nelson and the sculpture and the decorative building parts in Zhihua Temple. Different from the exhibition in Philadelphia Museum of Art, because of some of the small pavilions and the cloud decorated beams used to hold up the pavilion models were missing. The ceiling in Nelson only installed the main central square part of the temple room of Chinese Gallery. For the scanning process, the challenging mainly comes from 3 points. The first one is the huge size, and the second is the complicated decorated structure. As we seen from the right image, the whole ceiling surface is covered with beautiful hollowed out carving patterns. It means we need to use ultra high resolution scanners to record shape details. And as a result, this will lead to an extremely big data file. And for the narrow and deep dark portion, where even the light cannot be projected, there will be a lot of data missing. The third challenge is the high installation position. It means that we need to work on a high scaffold to reach the ceiling. And for reason of the structure light equipment, the staffs work on scaffold should keep static and move carefully to avoid any vibration during the scanner structure light projection. In order to make scanning process stable and efficiency, we separated the whole ceiling areas into 40 individual scanning parts. We carefully designed the boundary to each scanning range to avoid visual seams or gaps in later data alignments. As we seen from the right image, the ceiling do have obvious assembling clearance, and this provides us direct solution for scanning boundary designing, and it is helpful to avoid accumulated error. Based on the installation feature and scanning data requirements, we finally make a detailed scanning strategy, the roadmap, including the interior global space scanning and high-resolution scanning. The global scanning provides us global control points in the alignment process of the high-resolution fragments. This picture shows the position of each global laser scanning. Red numbers mark the scanning position. Black dots indicate the target ball for data alignment. Although the average resolution of global scanning is low, but it can provide us the whole accurate global space information. All scanning work executed inside the temple room, which shut off in order to keep the light consistent and throughout scanning and for the purpose of safety. These two shortcuts shows the original point clouds of the Central Dragon relief and side limb relief boards. It is obvious that there are lots of holes in the deep and occluded portion. As mentioned before, this problem caused by the basic principle of optics 3D scanning technique. As we can see from the principal image, if the area or surface cannot be projected or captured by structural light, and both of the fixed left and right measurement camera, the shape information cannot be calculated. In other words, the portion more open to the outer space, the easier the optical scanning. To solve the data missing problem in ceiling scanning, we developed a data optimizing method. And first, we applied semi-automatic hole filling tools to the missing parts. Left picture shows 3 types of data missing and the corresponding hole filling strategy. For complicated missing information, after hole filling steps, we use the digital sculpture software to modify the shapes, distortion with reference photographs. And this is the main software we used during the scanning project. And these 2 tables show the statistical features of the raw scanning data. We can find that both of the scanning data file exceed 100 GB, and it is quite difficult for data processing. These 2 pictures show some of the finished 3D data. This is a full view of the ceiling. In order to show its shape, we wipe the ceiling color information. This picture shows the Central Dragon carving of the ceiling. The left one is the raw 3D data. We can find out a lot of holes in the deep side. And the right is the optimized one after filling and shape revising. And this picture shows the limb dragon and the cloud decorated board of the ceiling. This is 2 of the decorated pattern in the triangle and diamond shape areas of the ceiling. Because of the limited working time for the ceiling parts kept in the storage, we use photogrammetry techniques to reconstruct the 3D shape and then calibrate the size by hand measure records. This cloud pattern decorated beams were used for small pavilion support. This is a central small pavilion originally located on the symmetry axis of the ceiling. This is a small pavilion model originally placed between the corner and the central pavilion. And the corner one. To reconstruct a full view of the environment, we also scanned the indoor sculpture in Wanfogge Zhihua Temple. For the other decorated building parts, such as corbel brackets and cloud decorated parts, we select the typical portion to extract the common shapes features in later reconstruction application. For the simple building objects, such as flattened wall, pavilion floor, regular columns and beams, because of their huge area and simple shape information, there is no need to scan them detailed surfaces. So we employ the laser scanner to measure the key parameter and then reconstruct the surfaces via 3D software. Even though we get the visible date of the ceiling objects, we still don't know how it be made and installed. To explore the question, we need to reconstruct structure behind the back of the behind the front surface of the ceiling. We know that the two ceilings exhibited in Nelson and Philadelphia Museum of Art were installed on the top of the exhibition hall. It is difficult to explain the back structure to visitors. However, for these two ceilings, the complicated structure and indicated the building process and is an important part of its historical value. To reconstruct the inner structure of the ceiling based on the 3D scanning data, we investigated the old photographs, published images, and other related documents. This photo plays an important role in the structure reconstruction research because all of the backside information were recorded clearly, especially on the right side of the ceiling. Several parts were being removed so that we can observe the inner structure clearly. In order to compare our reconstructed 3D shape with the old image, we need to figure out the direction and the exact position of the camera. It is easy to confirm the front side respected to the central Buddha sculpture if we pay attention to the horns of the central dragon and the Buddha orientation. We can find the horns pointing to the front side of the Buddha, and then the two overhang beams on the right each indicate the respective direction of the central dragon panel. While in the bottom right image, we cannot find these two overhang features based on the above clues. We confirmed the front direction is the right bottom edge of the ceiling in the photo. The next step, using the camera model in Autodesk Maya and the key points on the photo, we can calculate camera parameters by overlay the image to the virtual camera. The optimized criterion is the minimum distance of the key points pairs on photo and 3D model. This graphic shows the ceiling and the camera position. The word coordinate 0 points were defined on the geometry center of the bottom side of the ceiling and z-axis pointing to the front side of the ceiling. The table below shows the calibrated parameters and the camera position and the orientation respected to the ceiling. This is a calibrated camera view of the scanning data with overlay old photograph. These results will help us check back structure shape and is important to the structure reconstruction. What's more, there are 3 key planes which can be seen both from the front and back side. Because we already know the front information, the corresponding back structure position can be confirmed. The first plane is the circle ring part surrounding the central dragon. The second is the octagonal ring, the 8-lane relief board bottom edge, and the third plane is the bottom boundary of the ceiling. Then we can construct the structure one by one because the shape of the back surface flat and plane and the regular fundamental geometries, we can directly build the shape based on key parameters and then use Boolean methods to join the front carving shapes to the structure geometry. For example, for the top dragon panel, we can find the length and width ratio referred to the scanning data and old photograph. Well, for the thickness of these parts, we can confirm by overlay image to the camera. Using the same methods, we construct the other parts of the ceiling. The second part is the cloud pattern relief with the outside fixed frame. The circle ring made up of 8 parts. Each part also connected by precisely designed Falcon 6. Octagon dragon relief board assembly is the most complicated part in the ceiling. It's made up of 8 pieces of trapezium parts. This octagonal rings parts confused me a long time. At the beginning, we think this part is just a simple plain board with no groove, but we cannot explain the wedge block in the white circle. The block indicates there is a vertical gap between the lean dragon decorated board and the octagonal ring. Finally, we find a possible structure inspired by the backside structure of the ceiling in Philadelphia Museum of Art. The top side of the ring should be a stage-like structure so that the gap can be explained and the function of this structure will be more reasonable. For the main frames of the ceiling, its function is to connect, support it, and support the parts mentioned before. You can find the clues on the old photographs. And this picture shows how the beams and buttons connected together. The bottom frames consist of 4 parts in inner side of each frames decorated with cloud patterns and reliefs connected by Falcon 6 structure. This is triangle and the diamond-shaped cells. Each cell consists of many small parts because the time of limit of time, the detailed information cannot be discussed at this time. And this is a perspective full view of the ceiling structure. Under the plane light illumination. This is an exposure view of the ceiling structure. As we can see from the above figure, the internal structure of the ceiling itself is has a good aesthetic value and display for exhibition. This picture shows the final structure overlay on the old photographs. We can find that the model matches the images well. I want to emphasize that there is an uncertainty in the above analysis and conclusions, because without direct evidence, the strict estimation of the occlusion shapes is based on our experience. Let's get to the second part of this section, reconstruction of the installation environment. The left picture records the complete view of the Wanfo pavilion before the ceiling was removed, which is an important reference for us to rebuild the installation environment for the Wanfo pavilion. It can be seen from the figure that the main part of the ceiling is the small pavilion, the painting board, and the cloud decorated beams were all integrated together well. The picture on the right is the current situation of the Zhihua Temple. From the above pictures, we can find the installation position on the building. The first is connection between the main parts of the ceiling and the building. It can be seen from the photo that front and back edge of the ceiling are connected with the cloud pattern beams of the Wanfo pavilion. We reconstructed the frame structure of the building in the computer and restored the reconstructed ceiling to the beams of the cloud board in virtual space, and these two components matches well. For the small pavilions and the support cloud beams, we confirmed that none of the scanned beams length matches the building structure well. In other words, each of the original beams should made up of 2 or more separated parts. The 4-length beams should be like the above image. This picture shows the possible position of the existing cloud pattern board and the small pavilions. Restoration of the Heavenly Palace and cloud pattern beams. We also researched the order of the painted board. There are 4 types of paintings and shapes. One of them is square, 2 of them are rectangle, and the last style is triangle. The first 3 paintings types can be found in Nelson, and the triangle type can be found in Wanfo Ge. This picture shows the wireframe of the reconstructed 3D model. As I mentioned before, original 3D scanning data file is so big that we cannot directly put them together. To solve the problem, we use the texture technique to reduce the data, and at the same time, keep the same visual details. for reconstruction 3D model, the display application can be placed smoothly on website for online visiting. Okay, and last, let's have a look at some of the selected final shortcuts of the virtual reconstructed Wanfo. This picture shows the nature ambient light illuminate results. Sculptures and ceiling shapes can be observed clearly under this illumination condition. And another illumination test is about the time. Using the virtual lighting methods, we can simulate and experience the change of time in a day. Texturing the model will get a real and detailed view of the ceiling. And this is a final rendering results with color, texture, and normal map. Another view of the scenes, we add some frog effects to simulate smoke. And this image uses the camera post effects function to simulate the old photograph. And this is a front view of the central part. And last, how about scale ourselves to match the small pavilion and get there and walk around small pavilion to have a glance at the scene. This picture shows a new angle to experience an interesting world. Above all, digital technique in this project, in my opinion, not just possibly to combine separated things together, but also give us a new observed angle or even experience the objects. In the future, we're planning to finish the ceiling reconstruction in Philadelphia Museum of Art. On the other hand, based on the results, we want to develop a 3D interactive application used in the related museum exhibition. So let's expect our next research. Thank you for your attention. Thank you.